Hello, students. In this 1.1 Part 2 video, I'm going to talk about in details how to do elementary row operation to solve a systems from a augmented matrix. So you already learned how to write a systems into an augmented matrix form. Basically, put all the coefficient in the front and then the last row of constant in the right hand side, and we call it an augmented matrix. And our goal is to change it into a system by swapping the rows and multiplying the row and adding the rows together so that we have a upper triangular system, and then we can use a back substitution to solve it. So how do I go about, making an upper triangular system? So if you look at the numbers, you can see that this is row 1 and this is row 2. So if row 2 only have x2, then it become an upper triangular. So basically it would means I want to make this particular number 4 goes away. So I don't want to have 4. I want this to be 0. This 1 is okay, but I want to change it to 0. So how can I do that? If I multiply anything, it would not be 0, so I have to add something to it. The one thing that I can do would be to add something from R1, because this is the end of the row. But R1 only have 1, so what I can do is I multiply R1 by -4, so this become a -4. And if I add them, then this becomes 0. I don't care about other numbers, but this would make the goal of making the first 0 0. So I'm going to start by rewrite my augmented matrix. And then the operation that I am told to do is, or actually makes sense that I will do, is multiply R1 by -4, so they become -4, and I add R2 and I plug it back into R2. So remember, you cannot change R2 to any number if you are going to replace it. So the only thing you can do is you can add a multiple of another row. So I'm going to write the number here. So R1 multiplied by 4 become a -4. -4 times 12, -3 times -4 is 12, -1 times -4 is 4. And then I'm going to add 4 to 10. So this is the -4 R1 and this is my R2. And if I add them, I will have R1 stays the same, just copy, because I'm replacing only R2 by these 0, 14, and 14. So this is a new system, and you can see that this system is really easy to solve. Here, we just say that you do not solve, you just do the operation. But you can see that this is a upper triangular system, and you can solve it by back substitution. And we would have the same answer as the original one. Look at this system. Its system has 0 already. It has a 3, x1, x2, x3, right? And have 3 equation. So the only one that I want to get rid is this 4. How do I get rid of it? I can multiply. I would not use this to do not because of the 0 here, is because my first column is all 0 already. So I really don't want to add anything to make this non-zero. So don't use R1, but use R2. In R2, I would multiply it by -2, and then I add to R3 and put it back in R3. So this is how you say it. So that's how we do it. 0 to -3, -1. And I promise you that I will teach you how to use the calculator to do it in 1.2. So -2 times R2. So I'm going to do -4, 6, and 2. Plus R3, which is 0, 4, 1, 5. Plus R3. And replace R3. So you can see R1 and 2, I just copy. 2, 3, 0, 2, -3, -1. And I have 0, 0, 7, 7. So now this have 3 0 is an upper triangular system, and you would have x3 equal to something, x2 plus x3 equal to something, and you can do back substitution to solve. The third one that I want to show you is this one. I have, remember, for an upper triangular for 3 by 3 system, I have to have this 0, this 0, this 0. So I have to do 3 things. And in this, I'm showing you to do these 2 at the same time. Okay, so I want to get rid of the 3 by multiplying this by 3, but R1 by 3, and then replace it by R2. But because R1 is still stays the same, I'm multiplying it again by -1 and add to R3. You can see that that's the reason why we don't want to change R1 yet. We want to let it stay so we can use it to do that. So at this, but after you do this 2, 0, you still have to do the third one. So this is just practicing it. Let's do it. So we start off by just writing it. -3, 2, -3, -7, 1, 4, 1, 7. The first one, I'm going to do one at a time. 3R1 plus R2, put to R2. So it becomes 3, 0, 6, 3 times 5, 15. -3, 2, -3 is -7. It becomes 1, 0, 2, 5. R1 never change. 1, 0, 2, 5. After you add it, it becomes 0, 2, 3, 8. And then R3 we didn't change yet. Now we're going to do it. So be -R1 plus R3 put into R3. -1, 0, -2, -5, -5, and then 1, 4, 1, 7. So we would have a 1, 0, 2, 5, the OR2, 0, 2, 3, 8. And this one would be 0. Oh, I am changing R1. Right. And then so we have 4, -1, and 2. Right? Because this is -R1. And then I add to R3, 1, 4. So 0, 4. So you would have to get rid of this 4 here still. Okay. If you are to solve all the way. Let's actually do it. Okay, so we have this system. 2 equation, 2 unknown. So I'm going to write an augmented 3, -8, -1, 9, -1, -26. So basically just write all the coefficient and then just pretend we are doing the equation add and subtract. So now this is not 1. So some book would say you just divide all of them by 3, so it become 1. So, but because 3 and 9 are multiple of each other, so we can actually bypass doing that. We can just multiply 3 3 by R1 and then add to R2, put it back into R2, so we will have a 0 here. In case it is not a multiple of that, you would have to either divide this or look at if you can divide this first and then add. So there's different way of doing it. But usually in 1.1, we don't have those very difficult things. So -9, -3 times this will be 24, and then 3. Add to 9, -1, -26, and you will have 23 and -23. So 3, -8, -1, 0, 23, -23. So this is upper triangular. I would have x3 equal to -23. No, 23x3 equal to -23. So -x3 equal to -1. And then I have 3x1 minus x2. Oh no, this is not x3, this is x2. x2 equal to -1, right? So 3x1 would equal to -1 plus 8 times that would be plus -8. So that would be -9. 3x1 equal to -9, x1 equal to -3. So the answer is -3, -1. So that's how you do. After you have the upper triangular augmented matrix, you do back substitution to solve. Let's do a 3 by 3. So do the augmented matrix first. 1, 2, 1, 5. 0, -1, 1, -7. 1, 0, 2, -5. Hopefully it's fast. So I have 1 0 already done, so I just need to get rid of that. Negative R1 plus R3 equal, and then put it back into R3. So that would be negative 1, negative 2, negative 1, negative 5, 1, 0, 2, negative 5. So 0, negative 2, 1, negative 10. So I'm going to write it here. 1, 2, 1, 5. I don't change. R2, I don't change. 1, negative 7. And this would become 0, negative 2, 1, negative 10. So this one is the next one that I want to get rid of. To get rid of it, I use the second row, not the first row. Because if I add anything in the first row, this will come not 0. So use this, we call it the prefix position. This was the prefix position for eliminating. This is the second prefix position. If I multiply by negative 2 of R2 plus R3 and put it back into R3, that's what I will get. So I have 0 to negative 2, 14, right? And then I add to 0, negative 2, 1, negative 10. So that would become 1, 2, 1, 5 that don't change. My my R2 I don't change. 1, negative 7. But my R3 is now going to be 0, 0, negative 1, and 4. Right? So it is upper triangular, so I would have x3 equal to, negative x3 equal to 4. x3 is equal to negative 4. That's the first one. The second would be negative x2 plus x3 is equal to negative 7. So negative x2 equal to negative 7 minus x3, that's plus 4. So that is negative 3. Oops, so x2 is equal to 3. And then I get this first one, which is x1 plus 2 of x2 plus x3 equal to 5. So x1 would equal to 5 minus 2 times of x2, which is 3, also minus negative 4. Right? So this would be 5 minus 6 plus 4. That would be negative 1 plus 4 is 3. So the answer is 3 for x1, 3 for x2, and then negative 4x3. So that's the answer for, so that's how you solve a system by elementary row operation and back substitution. Okay, so maybe I'll talk about using elementary row operation to discover if a system is consistent or inconsistent. Like what we talked about earlier, consistent means it has solution. It can be one solution, it could be multiple solution. Inconsistent means there's no solution. So we're going to show you how to do that, okay, in the next video.